So we have one last intermolecular force that we need to look at, and then we're going to go through a few examples of how to determine relative boiling points and what intermolecular forces are present. So the last module I left off with saying as you increase in molecular weight, in general, you should increase the boiling point. Because I'm increasing molecular weight, I'm increasing the number of electrons, I'm increasing London dispersion forces, I should have a higher boiling point. And so if we look at this series right here, I see that as I go up in molecular weight from methane to tin tetrahydride, I have an increase in the boiling point of that molecule, right? Methane all the way up to there. However, if I look at the next series, the polar series of oxygen, sulfur, selenium, and tellurium, as I increase in molecular weight, I actually have the highest boiling point with the first molecule on this trend with water. Water has a higher boiling point than the sulfur, selenium, or tellurium, even though we're increasing the molecular weights of those samples. So why does water break this trend? Why does water have a higher boiling point than it should based on the molecular weight? Well, water breaks that trend because it has access to a new intermolecular force that is not available to other molecules. And that intermolecular force is hydrogen bonding. So water has access to an intermolecular force that does not exist in these other molecules shown here. That intermolecular force is a very strong intermolecular force, and that's what gives water a much higher boiling point than would be dictated by the molecular weight. So here is an example of hydrogen bonding. Hydrogen bonding is an intermolecular force between nitrogen, oxygen, or fluorine bonded to a hydrogen. So if I have a nitrogen, oxygen, or fluorine and it's bonded to a hydrogen, I have the ability to have hydrogen bonding. I could have hydrogen bonding between another nitrogen. I could have hydrogen bonding between another one of these elements, nitrogen, oxygen, or fluorine, right? I could have mixed hydrogen bonding. It doesn't matter as long as I have nitrogen, oxygen, or fluorine bonded to a hydrogen. This is what's going to set up the ability to have hydrogen bonding. Hydrogen bonds are set up much the same way that dipole-dipole interactions are set up. Nitrogen is much more electronegative than hydrogen, oxygen is more electronegative than hydrogen, and fluorine is more electronegative than hydrogen. And because of that, we're going to have a permanent imbalance where the heteroatom, nitrogen, oxygen, or fluorine, will always have a greater partial negative charge, putting a partial positive charge on the hydrogen, and that's allowing this hydrogen bonding interaction to occur between the hydrogen and another nitrogen, oxygen, or fluorine. And so like I said, we could have hydrogen bonding, right, between two identical samples. We could have hydrogen bonding between a mixed sample as well. It doesn't always have to be nitrogen, hydrogen, nitrogen. We could mix and match as long as the other atom is also nitrogen, oxygen, or fluorine. So hydrogen bonding, it's a little bit stronger. Sure, it comes in at 15 kilojoules per mole, but it's still a relatively weak force. But again, these forces are important because they're cumulative in nature. One very important example of where hydrogen bonding is important is between the nucleobases in our DNA. And so why does A pair with T and G pair with C? It's because they're hydrogen bonding complement. I get 3 hydrogen bonds between each guanine and cytosine in a GC pair, and I get 2 hydrogen bonds between adenine and thymine in an AT pair. That hydrogen bonding is what helps hold those strands of DNA together, and it's also what helps us figure out when I'm making a new strand of DNA, what is that sequence? I need to have the complementary sequence because it matches the hydrogen bonding pattern of the sequence that is there. If you have an error in your DNA, it's going to break that hydrogen bonding pattern. It's going to break the structure of that DNA. It's going to slightly change the structure of that DNA. So hydrogen bonding is incredibly important. One more example in hydrogen bonding, right? If you're like me and you do your laundry and then you forget about it in the dryer, it comes out all wrinkly and I don't really have time to iron it every day. That's an example of hydrogen bonding. So within the cotton, within your shirt, we have hydroxyl groups, and if you wash that, they're wet, they're high temperature, right, and then you just dry it and let it sit there, those hydrogen bonds set in any which way. And those are the wrinkles you see in that shirt. They're established by just a random hydrogen bonding pattern. Sure, you could reset that hydrogen bonding by ironing that out. So what do you need? You need high temperature, you need steam, and what you're going to do is break those hydrogen bonds and then reset the hydrogen bonds in a way that makes the shirt nice and flat. Another thing you could do, and this is what I do, is you could buy wrinkle-resistant material where they've chemically modified that cotton that goes into the material, and it breaks those hydrogen bonding interactions. It prevents those hydrogen bonding interactions from occurring, and it sets the fabric at that uniform distance apart, preventing the fabric from wrinkling. So here's a question for you, kind of summarizing all the intermolecular forces that we've worked through. Got 4 different molecules. We've got a molecule of butane, acetone, ethylamine, and acetic acid. And I want you to figure out what are all of the intermolecular forces available to each of those molecules. So the molecule of butane, what intermolecular force do we have present? Well, if we take a look at butane, do we have ions present? No. We're over here on the left. Are polar molecules present? No again, because we just have carbon and hydrogen. So the only force that butane has available is London dispersion forces. If I look at the next molecule, acetone, do I have an ion present? No. I'm still on the left side of this chart. Are polar molecules present? Yes, we do have a polar molecule present because I have a carbon-oxygen double bond. Oxygen is more electronegative than carbon, and because of that, I'm going to have dipole-dipole forces. I do not have hydrogen bonding because I don't have an oxygen bonded to a hydrogen. I just have carbon bonded to that oxygen. So all molecules have London dispersion forces. This molecule also has dipole-dipole forces. If we take a look at the ethylamine, well, I said previously all molecules have London dispersion forces, so we can answer that for the next 2, ethylene, ethylamine, and acetic acid. Are polar molecules present? Yes. We have a nitrogen bonded to a carbon, and we have a hydrogen bonded to a nitrogen. Nitrogen is more electronegative, and that's going to create a polar molecule. So yes, we have dipole-dipole forces. But we also have an additional force because not only do we have a polar molecule, we also have nitrogen bonded to hydrogen, which means we have hydrogen bonding interactions as well. The same with acetic acid. We have a polar molecule because I've got an oxygen bonded to a carbon. That's a polar bond, so I'm going to have dipole-dipole forces. And I also have oxygen bonded to a hydrogen. That's going to set up hydrogen bonding interactions as well. So all molecules have London dispersion forces, and then from there we have to figure out, is the molecule polar or not? If it's polar, we're guaranteed to have dipole-dipole forces. If it's polar and has a nitrogen, oxygen, or fluorine bonded to a hydrogen, then I'm going to have hydrogen bonding interactions as well. Here's one more chart to think about how we can compare the boiling points and kind of summarize everything that we've talked about today. So if I look at the first series of alkanes, I go from 3 carbons all the way up to 6 carbons, and I see an increase in the boiling point from minus 42 degrees Celsius all the way up to 69 degrees Celsius. So across that series of alkanes, why do I have an increase in boiling point? I have an increase in boiling point because I have an increase in molecular weight. All of these alkanes are nonpolar. They all have only London dispersion forces, so increase in molecular weight causing an increase in London dispersion forces and an increase in boiling point. So that's if I compare this series right here. I have an increase in boiling point because I'm getting a larger and larger molecule, more electrons, more London dispersion forces, higher the boiling point. And I see that same trend here and that same trend here. If I go from left to right, I see an increase in the boiling point of that sample because the molecule is getting larger and larger and larger, more electrons, more London dispersion forces, the higher the boiling point. The next comparison would be, let's go between a couple different groups. And so if we pick a couple different groups and say, let's compare the boiling points of these 3 molecules. Why do I have an increase in boiling point as I go from pentane on the top, pentanol in the middle, and pentanoic acid on the bottom? So I would explain this increase in boiling point due to stronger intermolecular forces. Right? The molecule on the top has the lowest boiling point because I only have London dispersion forces. The second molecule, I have London dispersion forces, dipole-dipole, and I have hydrogen bonding. For the third molecule, I have an even higher boiling point because you'll notice, right, I've got more opportunity for those dipole-dipole forces. Here I've got 1 bond that can do dipole-dipole forces. With the pentanoic acid, I have 2 bonds that can involve dipole-dipole forces, and I have hydrogen bonding as well. So I have all 3 plus some extra dipole-dipole forces. So those are the 2 comparisons you'd be asked to make. If I'm asking you to explain a difference in boiling point and all the molecules have similar intermolecular forces in this first series, right, then you're going to explain that increase in boiling point based on increase in molecular size, increase in electron cloud density, and increase in London dispersion forces. The second trend, we'd explain the second trend by increasing boiling point due to stronger intermolecular forces. We see a large jump from number 1, pentane, to number 2, pentanol, because I've added that hydroxyl group. I've added the ability to have hydrogen bonding and dipole-dipole forces. Those are stronger forces. I have to break those forces now to go from the liquid phase to the gas phase. That's going to result in an increase in the boiling point of that sample. So you should be able to identify hydrogen bonding, dipole-dipole interactions, London dispersion forces, and ion-dipole interactions. You should know the relative strengths as well, right? Hydrogen bonding, ion-dipole are the strongest forces. London dispersion forces, all molecules have those, but those are the weakest forces, right? Individually, these are very weak, but cumulatively they're very important. They're going to help determine the properties of a molecule, things like the boiling point and the viscosity of a molecule. So our next lecture, we're going to take a look at phase diagrams. So how do these phases of a sample change over different temperatures and pressures, as well as looking at the energy involved in some phase changes.